Hello, and this morning I'm going to go through how we've ported the OpenJDK to use Cheri capabilities to prevent certain security bugs, such as in this case the exploit and demo is going to be showing a buffer underflow. So why don't I just jump right into it and start describing what this buffer underflow is. So the CVE was from 2015, and I've just kind of showed a simplistic view of what our memory layout for this program I'm executing is. So on the native heap, we have this int buffer filled with Bs, and then on the Java heap, we have this dest int array filled with As, and then we also have this int array before the dest array just filled with BAs. It's quite a simplistic view of what the memory layout is, obviously, but this is also what the memory looks like for epsilon GC. It's slightly more, and epsilon GC being the GC that allocates but doesn't actually collect. It's slightly more complicated for serial GC because that is actually a collection GC. So yeah, how does this underflow actually happen? So the security bug is actually on this ib.get function, where we're copying these Bs into the destination, this dest array being this orange array here. Then we can have this dest offset, which is an offset into the array, and the length, which is how much you want to copy from this int buffer array. And we can actually cause an underflow on this dest offset, which means that we end up copying before the dest array, so we end up copying into this int array here. And what I'll show you later in the demo is that you can see this unsafe copy swap memory being called with a negative offset. So just this little diagram under here, it just shows you our happy case. What we want to happen is that we want to copy from a source array into the dest array, and this is what should be happening. But because there's this exploit in this code, I can actually copy from the source array to before the dest array. So I'm copying these Bs into this BA array, and I shouldn't be able to write here, but because of this security bug, this buffer underflow, I have been able to do this. So whilst we were porting the JVM to use Cheri capabilities, with GC we've kind of gone through 3 different scenarios. Scenario 1 is that all objects have heap-wide bounds on the Java heap. And this is the case because the Java heap is block allocated, which means it just allocates one giant block for the heap through a malloc call, and then that is it. The JVM has its own allocators and its own GC, and that is all handled with the JVM itself. Which means using Cheri capabilities by default doesn't protect this underflow, because any object can access any other object on the heap. Our next scenario we went to is constrained but overlapping bounds on large objects. So why do we have these overlapping bounds? We have these overlapping bounds because of Cheri bounds compression on these capabilities. So for larger objects, you don't get the granularity for your bounds. So the bounds between objects that are next to each other on the heap actually overlap. So I'm kind of just showing you this crudely with kind of this these overlapping bounds here for this int and this dest array, which also means that this underflow I was showing you on the page before isn't actually prevented because we can still write to this int array, which is before the dest array. One thing I do want to highlight is that I'm actually using extremely large arrays to do this exploit, because I need the arrays are really large because I need to cause that in underflow on the dest array offset. So this is why in this case we have really large overlapping bounds, because we have really large objects. So now let's go on scenario 3, which is what I'm actually going to be demoing later. And this is where our bounds are constrained exactly. So this means that you can't write before the dest array, and that all objects on the Java heap only have access to themselves. And yeah, this prevents the underflow that I was showing you before, and it causes a sigprot, which is a Cheri protection violation. So I guess we'll go straight into the demo. So I've got 3 different things that I want to show you. The first being what happens on our template Morello JDK with heap-wide bounds. So I just want to go through in GDB what the exploit actually is. The next one is what happens when we run this exploit on our JDK with these constrained bounds. And this is using serial GC, but for template it also works for epsilon GC. And then I also want to show you what happens for 0 Morello with exact bounds. Again, this works for both serial GC and epsilon GC, but in this case I'm just going to show you serial GC just because serial is a more complex GC algorithm here. Just as a part of information, what's the difference between template and 0? 0 is kind of all written in C++ code, making it platform independent, whilst template has assembly code. So 0 is a lot slower than template. So I'm actually going to set off our 0 run before I go into the top 2 template examples and showing you what's happening in GDB itself, just so that we're not sitting around and waiting for that program to finish for a while. So I think I should have it here. Yeah. So yeah, what you see here is that I'm using serial GC, and yeah, I'm just running this program that we've set up. So yeah, I'm just going to set that off, and then I'm going to go into this template Morello no bounds example. So this is where I should be able to exploit this vulnerability. So yeah, in this case I'm using epsilon GC just because, as I described earlier, this has a simpler memory layout, so it's kind of a lot easier to visually demonstrate what's happening. So I'll just set off. Actually, I'll make the screen bigger. Cool, that should be good. But yeah, before I set off, I should put some breakpoints in. So I'm going to pop up breakpoint in unsafe copy swap memory, which is a function I defined, just said earlier, and then also breakpoint in this copy swap memory, which is where you can actually see the dereference happening. So yeah, I'm just going to run that. So this unsafe copy swap memory, which we should be hitting first, you can see it being called with a negative offset, which means I've already caused this the first stage of this buffer underflow to happen. Cool. So we've actually hit this breakpoint. Yep, you can see the name of the function copy swap memory. A lot of other stuff like the source object, dest offset object, but what we're more interested in is what this dest offset is. Sorry, the D's been slightly cut off there, but yeah, what you can see is it's being called with an exit offset of -192. So let's continue on into our next breakpoint. So this is where we can actually see the dereference happening. I'm just going to skip a few lines down to where the dest is being dereferenced and set to temp. Temp being this B array that we have here for the int buffer, or B's in this case, that we got from the int buffer. And then let's just print out current dest so we can see its bounds. See, what you see here is that current dest has this address, but it also has heap wide bounds. But why don't we just have a look at what is stored at current dest? Because in what we would expect to be at current dest is A's. But what is shown here is that we're actually at BA's, which means that we're actually at this int array rather than the dest array. And just because I know the offset is -192, I can just add 192 to this. And yeah, so this is just array header information, and then you can actually see we have our array filled with A's, which is what we'd expect from here. So this is just showing you that the address of current dest is currently not pointing to the dest array, but before the dest array. Which means when we dereference and set the temp to be that, we're actually writing to the array before the dest array. So I'm actually just going to continue this program until the end now, just because I've kind of gone over that briefly, what's actually happening in this code. And yeah, I've just popped in some helpful printouts here, which shows you, I'm just looping over the end of the BA array, so the array before the dest array. And what you can see is I've copied some B's into there, so I've been able to write to where I shouldn't, and I've put this very handy overflow with some exclamation marks just to make that a bit more explicit. So as you can see is that we are using Cheri capabilities, but by default these Cheri capabilities do not give us the memory protection for the Java heap. So yeah, that's kind of what's happening when we just have heap-wide bounds. So why don't I show you what happens when we have exact bounds? Again, I'll make that screen larger. So this is where our objects don't actually overlap. I'm using serial GC, which means that our arrays aren't going to be aligned in memory as they were very nicely in the example I just showed you before on epsilon GC. But yeah, let me just pop those two breakpoints in I did before. And let's run this. So this is template Morello with exact bounds using serial GC, running the exact same code that the no bounds program was running. Cool, so we've hit that breakpoint. So yeah, first thing I just wanted to highlight is that this dest offset is still negative. So the patch that was put into the JDK, this offset wouldn't be negative anymore because this buffer underflow, this underflow of the int wouldn't actually be able to happen. So this shows that we still don't have that patch they put into the JDK to prevent this exploit from happening, and that everything we see from now on is protected via our porting of the GC and use of Cheri capabilities to constrain the bounds of every object on the Java heap to itself. So yeah, yep, I'll just continue on to the next breakpoint. So the same breakpoints as before. Let's do the same as we did before and copy down to current dest. So yeah, let's have a look at the bounds of current dest. So what we see here is that the bounds are a lot smaller. Well, they are small because it's a really large array, but they're a lot smaller than they were before. They're no longer heap wide. Yeah, so I can also, well, I think that's pretty much all I wanted to show you, just because if I did what I did before, current depth is not, actually, sorry, 20x. So this is just pointing to somewhere in the heap. It's not pointing to the same object as before, because as I said, these objects no longer align in memory because I'm using serial GC. So why don't I just continue down, and hopefully would see the sig prop, which is on this line of code that I was showing you here. Because as you can see, this address is actually outside the bounds of the capability, which means that when we try and do reference and assign temp, which is our B array, we expect a Cheri protection violation fault, because we shouldn't be able to write here. So in essence, we've been able to protect against this buffer underflow and prevent the write from happening. So this is a very simple example, but these buffer underflows can be used to like cause type confusion, which means that you can kind of like start hijacking the class load of a security manager, and a lot of other things. But this is obviously a very simple example where I'm copying B's and A's to where they shouldn't be. So yeah, let's just exit GDB and go back to that 4 screen. I just wanted to show you that this was the 0 Morello with serial GC, and what you can see is that we got exactly the same Cheri protection violation, which means, yeah, I just wanted to show you that both on 0 and template for our ported JVM has this GC protection that we've added in. But I think that's all from me. So thank you for listening and have a nice day.